So we have a circuit of the three resistors, 3.3K, 4.7K, 10K resistor. We have one current meter measuring the total current going into the network, and then we have to move the meter to measure the branch current in each resistor one by one. And we'll put those results into a table and check to confirm that the branch currents in fact add up to the total current for the circuit, therefore confirming Kirchoff's current law. Just as we've done previously, the very first thing to do is confirm that we have the 9 volts at the supply part of the circuit. So you can see there 9 volts. I've used the Fluke multimeter to confirm that is the correct voltage before we go ahead. Now I'll have to move the leads on the multimeter and go from voltage to current, and then we'll proceed to do what's set out in the lab, and that is to measure the total network current in the lab. I've done some maths before proceeding, and I can see that with the 3 resistors in parallel I have an REQ of 1623 ohms. That is equivalent resistance. The current's going to be equal to the voltage over the total resistance, so that would work out to be 5.54 milliamps. From the calculations now, I can go ahead and look at what the current meter actually gives me, and I can see I've got 5.58 milliamps. I'm out by a little bit, but not too much. That's probably just standard tolerance within the resistors, and of course perhaps some drop in voltage because of the resistance of connections in the circuit. I've transferred that total current that we just measured across into the measured total current section on the first table, table 1. Be careful when you're measuring the current. It's really vital that you think about how you're going to set up the meter. When you're setting up the meter, you have to actually break the circuit. So what I've done here, I'll just sort of unwrap this. I've taken the 9 volt power from the power supply and I've put it to a blank terminal on my board, and then this is the terminal that goes into my circuit. So I need to put the current meter between the positive 9 volt lead and the beginning of the circuit. The beginning of the circuit will be the negative lead on the current meter, and the 9 volts would be the positive lead on my current meter. And then we already saw I had 5.59 milliamps of current measured into the circuit. Now I'll go ahead and I'll start putting the circuit back the way it was. I've got the 9 volts coming in now, supplying all 3 resistors, but the table calls for us to measure the individual branch currents. So I'll do that by first of all disconnecting the 3.3k ohm resistor, and then we'll have a look at how we measure the current going through the 3.3k ohm resistor. I've put the positive lead from the milliamp meter back onto the 9 volt positive terminal. I have the 3.3k resistor disconnected from the network, and now I'll use the negative lead on the current meter directly onto that 3.3k resistor. So all the current is coming from the 9 volt supply and going through the current meter. The current meter tells me I have 2.77 milliamps DC current flowing through that resistor. So I'll write that down into my table. Now that I've done that, I've recorded that current going through the 3.3k ohm resistor. I'll put the 3.3k ohm resistor wire back into the circuit, and I'll proceed to disconnect the next resistor, the 4.7k. And then I can take a reading of the current going to the 4.7k resistor by putting the black lead of the multimeter onto that resistor. It tells me I have 1.92 milliamps DC current, so I'll record that on the table. Finally, I measure the current going through the 10k ohm resistor. The current going through the 10k resistor measures at 900 microamps DC. Now I'll record that on the table. After recording all of the measured results, we find that the total for the measured individual values certainly adds up to the measured total current. The calculated values are slightly different than the measured values, and that leads me to think that the resistors might be quite significantly different to what the colours show that they should be. The first resistor, then, I've got the DMM connected as a resistance meter, and I'm measuring the resistance now across the 3.3 resistor. The 3.3k resistor is in fact measuring at 3,249 ohms. Again, we measure the resistance across the 4.7k resistor. The 4.7k resistor is measuring at 4.67k. The 10k resistor is measuring at 9.95k. In the last question on page 40, we're asked to write down Kirchoff's current law. I've written here simply the sum of the branch currents adds to equal the total network current of that parallel network. In part 2 of the lab, we have to transcribe the values we took from table 1, which is the total circuit current and all the individual branch currents. Now what we have to do is open up the 4.7k ohm resistor and then get the new total circuit current and the new individual branch currents. So I've done that. I've opened circuited the 4.7k resistor, and the new circuit current reads 3.6 milliamps. Now with the 4.7k resistor still open circuit, I'm measuring the branch current of the 3.3k resistor. That comes in at 2.77 milliamps. Now with the 4.7k resistor open circuit, I'm measuring the branch current of the 10k ohm resistor. The 10k ohm resistor comes in at 900 microamps. I go ahead and I record that in table 2. It starts to become quite clear that although the total circuit current has changed, the individual branch currents for the resistors that were not open circuit remain the same. I'll go ahead and I'll do the last row in table 2. The last thing to do in table 2 is to open circuit the 10k ohm resistor and measure the total circuit current. I've done that and I measure 4.68 milliamps. I've transferred that 4.68 milliamps into table 2 and I measured the branch currents from the other parts of the circuit to complete table 2. And this time I found out to confirm that I still have 2.77 milliamps regardless of what I do with the 4.7k resistor or the 10k resistor. Only the resistor that we open circuit, of course, that particular branch will then have zero current flowing in it. The last question in the lab asks us to answer the reason why we never put a short circuit across a branch in a parallel network. Well, effectively, if we did that, we'd be placing a short circuit across potentially what could become a large amount of current flow and cause quite a bit of damage to a circuit. If there is a fuse, of course that fuse will blow. And to demonstrate that, I've got our same 3 resistor parallel network set up, and I've used a wire across the network in which I'll perform a short circuit operation. I've got a fuse now in line with my circuit, so I'll go ahead and I'll short circuit the 10k ohm resistor and note what happens. Of course the fuse blows straight away and there's no voltage then supplying the circuit. Luckily the fuse acted to protect any other components in the power supply. I've placed a fuse in line with my network of 3 parallel resistors. just to demonstrate what would happen if I do place a short circuit in a parallel network, watch what happens to the fuse. Of course, the fuse blows straight away and there's no voltage then supplying the circuit. Luckily, the fuse acted to protect any other components in the power supply.